In this chapter, we're moving on to talking about different functions. And the two functions that we are interested in this chapter are exponential functions and logarithmic functions. So in this lesson, I'm going to talk about exponential functions. A couple of basic things about an exponential function is that you can think of it as a number being multiplied by a power. So notice that the number that's being raised to a power, the b that has the exponent, it needs to be positive. So if you see something like this, realize that it's actually this, and then kind of treat it like from there. So how do I graph these? Basically, it's just plug in a couple of values. The intercepts and asymptotes and end behavior and so on and so forth we'll talk about after we've plugged in a few values. So if I plug in -1, 0, 1, I think I made these tables have too many values. So if I plug in -1 for x in part 1a, then I'm actually taking 6 to the first power, which is just 6. If I plug in 0 for x, then I'm taking 6 to the 0 power, and something that's very, very, very important for you to know and remember is that anything raised to the 0 power is 1. So you're going to see 0, 1 as a very, very common y-intercept. So if I plug in now 1 for x, I'm taking 6 to the -1 power. And another thing that you want to remember from algebra is when you're taking something to a negative power, you're taking the reciprocal of it. So taking 6 to the -1 power actually gives me 1/6. So this is enough for us to get a general idea of the shape of our graph. At -1, it's passing through 6. So 1, 2, 3, 4, 5, 6. Here. 0, 1, and then 1, 1/6. And what I'd hope that you'd realize is that as the values, for example, if I plug in 2 here, I would have 1/36. So the larger and larger my values get in this function, the closer and closer I'm getting to 0. So this graph looks like this. And it's flattening out towards that 0. On the other graph, very much the same values for x would be good to plug in. So -1, 0, and 1. And when I plug in -1, that gives me 1/5. Plug in 0, I get 1. I plug in 1, I get 5. Take those values and plot them. I have -1 is 1/5, so that's there, 0, 1, and then 1, 5. So you see it's pretty much the same idea, just going in the opposite direction. So once we sketch the graph, it's asking us to describe all these properties of it. So my domain for this graph is all real numbers, so -infinity to +infinity. My range for this function, notice that it never goes below the x-axis. Notice also that it never actually hits the x-axis. So my range is parentheses 0 to infinity. What else is it asking? It wants to know intercepts. So I've already mentioned that it never crosses the x-axis, So I know I don't have an x-intercept. I also mentioned earlier that the y-intercept for this function is a very common y-intercept. You're going to see a y-intercept of 0, 1 very frequently with these functions. I mentioned also that it's getting closer and closer to the x-axis, but it never actually touches it. So I have a horizontal asymptote of y equals 0, also known as the x-axis. End behavior, as x approaches negative infinity, my f of x is approaching, remember what you're looking at. As x is approaching negative infinity, that means I'm looking towards the left side of my graph. And on the left side of my graph, the further left I go, the higher up I'm getting. So that's positive infinity. As x approaches positive infinity, f of x approaches, well, I mentioned the further right I go, my graph is flattening out towards 0. Finally, I'm asked where the function is increasing or decreasing. I'd hope that you'd notice that this graph is decreasing from negative infinity to positive infinity. So for negative infinity to positive infinity, it is decreasing. And they want us to analyze the second graph in the exact same manner. And what I'd hope that you'd notice is a lot of this stuff is going to carry over. So my domain, again, is negative infinity to positive infinity. My range, again, is from 0 to positive infinity. Remember, with range, we haven't talked much about range recently, so let me refresh your memory. If we think of domain as a vertical line being dragged across our graph, remember that means we think of range as a horizontal line being dragged up our graph. And that horizontal line being dragged up our graph wouldn't hit our graph until approximately 0. It'll never actually hit zeros, which is why I have a parentheses there and not a bracket. So you could think of 0 as kind of a soft boundary. And then if I continue dragging that horizontal line up my graph, it is crossing my function until infinity. Once again, my y-intercept is 0, 1. My horizontal asymptote here is, again, y equals 0. My end behavior is pretty much the exact opposite as the function I have graphed in red. So as x approaches negative infinity, f of x is approaching, again, realize what you're looking at. The further left I go, what is my function approaching? My function values, my y values, are getting closer and closer to 0. Whereas, as x approaches positive infinity, my function values, my y values, are approaching positive infinity. And then finally, for the interval negative infinity to positive infinity, it is increasing. And we transform these graphs in exactly the same manner as we transformed graphs in Chapter 1. We still have h values, we still have k values, and you just have to remember what you learned back then. H's move things sideways and do the exact opposite of what you would expect, and k values are straight shooters and they are vertical change. Okay, so if I consider this my parent function, and I realize a few points that that is going to go through, it's going to go through -1, 1/4, 0, 1, and 1, 4. So if I consider those 3 points, what I'm basically looking at is how am I transforming those 3 points based on the additional h or k or positives or negatives thrown in. So in part 2a, I'd hope that you'd notice that this is a k value, which means it's moving down 2 spaces. So I'm going to start with the y-intercept and kind of move things from there. This 0, 1 is going to go down 2 spaces. So it's not going to be at 0, 1. It'll be at 0, -1. The 1, 4, well, it won't be at 1, 4. It's going to come down 2 spaces. So it'll be at 1, 2. Finally, this -1, 1/4, well, it won't be there either. It's going to move down 2 spaces. So it'll be at -1 3/4. Here. And then if you remember that 4 to the x power is going to behave very much like this graph that had a horizontal asymptote at y = 0. This will have a horizontal asymptote at y = -2. So I might want to make sure that I'm coming from flat there and growing very big very fast. Part B, couple of more things are happening here. I don't have a k value. I do, however, have an h value. H is -2. Remember, h values are the opposite of what you see. So this graph is moving to the left 2 spaces. Also, notice the negative out in front. Remember what that's doing to our graph. It's flipping it upside down. Make sure that you realize it's not flipping it sideways. My A is negative, not my B. Okay? So, I start with these points again. And since I already have that -1, 1/4 underlined, I'm going to run with that. That is going to be flipped upside down, so it'll be at -1, -1/4, and then moved 2 spaces to the left. Okay, so let me go through this whole process because there's a couple of things going on here. When I take that -1 to the 1/4, I'm referring to this point here. When I take the -1, 1/4, and reflect it over the x-axis, it would be here, approximately. But then because of my h value, I'm going to take that and move it 2 spaces to the left. So now it's here. The 0, 1, when I reflect it over the x-axis, it would be 0, -1 here. But then again, because of my h value, I'm going to march that 2 spaces to the left. It'll be here now. Finally, the 1, 4 would be at -1, at 1, -4 here. But again, because of my h value, I'm going to take that point and move it 2 spaces to the left. And now it'll be here. I can't undo erasing. I'll do that again. So it was here, and then I marched it 2 spaces to the left, and now it's there. And then I basically make my curve. A lot of times the exponential function e to a power is important to us. And the main thing you want to know about e is that it's used when we're talking about an interest rate or a decay, something, either growing continuously or decaying, being compounded continuously or decaying continuously. As far as its value goes, it's kind of one of those values that you get used to using frequently, kind of like pi. It's approximately 2.72. Okay, if you can remember 2.7, then that's good enough for me. And besides which, your calculator has an E button in it. So the main thing that we're looking at in example 3 is just transforming that E function, just like what we did in the last one. Now you notice I don't have a grid here because E is such a nasty value. To take it and raise it to a power and get another nasty value, I'm not terribly interested in the precision of the graph as much as I am in the shape of the graph. Okay, so the main thing that I kind of want to talk about on this screen is not so much what its graph would look like, but the transformation of it. Okay, so e to the x looks very much like maybe this red graph that we did. It has that shape. It's not in the exact same place. It kind of resembles this blue graph over here. Resembles that shape. Okay, so the main thing I'm interested in example 3, part A, is realizing that this will be reflected over the y-axis and it will be horizontally condensed. Okay, so if my E function looked like this, then this one would kind of have a steeper growth and it would be going over the y-axis. So it would kind of look like this. That's the main thing I'm interested in this problem. Because E is not a nice, pretty number to graph, I'm not going to spend a lot of time with the precision of the graph. Okay, finally, if my basic parent function for E looked like this, e to the x minus 5 would just be 5 spaces down. So 1, 2, 3, 4, 5. That's the main thing I'm interested in. Okay? believe me, we will have plenty to do with E that is more important than graphing it. Like finding how much money you're going to have in your account based on whether it's compounded semi-annually, quarterly, or continuously. And we'll get to that formula a little bit later. Right here, we're using this formula for when we have a specific number of times that your interest is getting compounded. Okay, so I have $1,000 investing in a savings account. It's earning 8% a year. I want to find out how much money I'm going to have after 10 years, assuming there are no other deposits or withdrawals. So in part A, it's saying semi-annually. And what I'd hope that you'd realize is that it's being compounded 2 times a year. So looking at this formula up here, that T is how many years the T is years, and then the N is how many times a year it's compounded. So the N in my formula is going to be 2 for part A, and the T for parts A and B will be 10 for 10 years. What you want to make sure that you're cautious of is that your interest rate is expressed as a decimal. So remember how to do that. You're moving the decimal point 2 spaces to the left. So there we go. My amount will be 1,000 times 1 plus 0.08 over 2 raised to the 2 times 10, which is 20th power. So if you are still using my little blue calculators in class, that's not going to help you here. You want to make sure that you at least have a scientific calculator. So using my scientific calculator, I have 1 plus 0.08 divided by 2 raised to the 20th power times 1,000. And at the end of those 10 years, I will have $2,191.12 approximately. In part B, if my interest is compounded quarterly, that means it's compounded 4 times a year, so my N is 4, and we're plugging into the same formula. So I'll have that my amount will be 1,000 times 1 plus 0.08 over 4 times 4 times 10, which is 40. And the rest is just calculator. At the end of 10 years, I will have $2,208.04. So you see a little bit of an increase of how much money I will have in my account if my interest is compounded quarterly versus semi-annually. Take a moment and work through the your turn below, part C. So what if my interest is compounded continuously? And that kind of means that my money is constantly getting compounded. That's where E comes in. And the formula is nicely condensed to this A equals PERT. So we plug the values into the formula. My amount will equal 1,000 times E raised to the 0.08 times 10 power. And that will yield $2,225.54 approximately.